Hello everyone and welcome back. Now in the previous video, I introduced you to a Cantor set that arises as a fractal invariant set to the logistic map. And this was in a parameter regime that you probably don't encounter very often. That's when mu is larger than 4. And that comes from the fact that if you try to simulate this thing on the computer, you're not going to see it. That fractal set, which is a dust, right? It's a collection of like almost nothing within the interval 0 to 1. That thing is a repeller, right? If I start very close, if I don't have the exact digits right, boom, sensitive dependence on initial conditions, goodbye, right? So what we would like to do in this video is come up with an abstract way of thinking about the dynamics inside of this Cantor set. Now, what we're going to do is introduce what's called symbolic dynamics, these sequence spaces. And then when we come to the next video, we're going to put these two things together. So this video is going to feel a little bit abstract, but it's also very cool. If you're really into chaos theory, which I am, obviously, symbolic dynamics is one of the funnest things that you can play with because it's so simple, and yet it's so perfectly beautiful in how it captures really complicated phenomena. And here's what I'm going to start with. I'm going to start by defining a sequence space, okay? So I'm going to do sigma sub 2, and this is going to be the set of all possible sequences. I'll call them S. They're going to be by infinite, so they can be indexed by the non-negative integers. They go on forever, and each element is just 0 or 1, okay? So this is why I have the sub 2 here, right? These are binary sequences between 0 and 1. Of course, if you wanted to, you could have trinary sequences or hexadecimal sequences or whatever it is. Typically, we call these things the symbols, and you just talk about having a finite number of symbols. In our case, we're going to use the binary case, so symbols of zeros and ones, because that's the simplest that we can do, to at least for presentation. Okay, so I have a space, right? Mathematics, we talk about spaces of things. These are sets. They're collections of like objects. In my case, my like objects are a bunch of sequences. Now, what I would like to do is I would like to be able to talk about relationships between these sequences. And I would like to talk about how far apart they are. So I'm going to introduce a distance or a metric on the space of all sequences. So it's going to be a distance for D. Sequence S and sequence T go into this thing. And the way that we compute the distance between them is we are going to look at a weighted sum of the difference of their elements. Okay? So what you can see here is that we are weighting each entry. So the first entry of the sequence gets the largest weight, right? It has 2 to the 0. And then the next element of the sequence is the second most important. The third element of the sequence is the third most important, and so on and so forth. The 100th element here is not really all that important, right? This thing is the decaying metric. And essentially, what we can see here is that this element, right, this Sn minus Tn, because these two things are between 0 and 1, this thing has to also be between 0 and 1. And what that immediately tells us is that the distance over this entire space, right, dst, is less than or equal to 2 for all S and T in sigma 2. Right? So everything in this space is no more than 2 units apart. And that comes from the fact that, the worst case scenario is you have a sequence maybe of all zeros and a sequence of all ones. Everything is 1 unit apart from itself, and then you just get the sum of 1 over 2 to the n, which sums to 2 in our case. So in fact, this thing becomes a distance on the space, on this sequence space. So maybe one thing that you could do is you could introduce a proposition, and you could say ds of t is a metric on sigma 2. And again, if you've encountered this as in real analysis, that means that sigma 2 equipped with this distance becomes a metric space. And effectively what this tells us is there's a way of measuring distance between objects. Now this distance here we've sort of spoken about. Now the first thing that we can see is that, of course, so maybe the proof here, ds of t is always non-negative. So that's the first condition to be a metric on the space, right? You can't have a negative distance between objects. And the only way that this thing can equal to 0 is if S and T are exactly the same object, right? So everything is separated in this space. The only way that you can have 0 distance between two objects is if they are the same object. And the last piece of this is the triangle inequality. So one of the defining features, S to T plus D, the distance from S to T is less than or equal to the distance from S to U plus the distance from U to T. And where this sort of comes from is it comes from traversing a right angle triangle effectively. So if this was S down here and this is T up here, then the distance from S to T is shorter than the distance of taking an intermediary stop at some other point U, okay? So this is just the definition of a metric or a metric space. So we don't have to worry about it too much. But the point is, now I have a way of measuring distances on this space. In fact, something that's going to be very important for us going forward is we want to classify when two elements in this space are very close together. So let's say let's take two sequences from the space such that Sn is equal to Tn for all n equal to 0 to, let's say, capital N, okay? Then the distance between these two objects is 1 over 2 to the capital N plus 1, okay? Is, sorry, less than or equal to 2 to the capital N plus 1. So at most, so this thing is, could be a very small number. And conversely, if this distance is this close, 2 to the capital N plus 1, then these two things have to match. Tn is equal to Sn for all n equal to 0, 1, all the way up to capital N. Okay, so take a look at what that says. It says that if your two sequences match for the first n plus 1 digits, then these things are going to be within 1 over 2 to the n plus 1. And that's an easy thing to prove, right? Just basically the first, from 0 to capital N, these terms are all going to be 0 in here. And so then you just sort of repeat this argument, but it's going to be, the n plus first term here is going to be 1, maximum of 1 over 2 to the n plus 1. Okay, so that's easy, right? Sorry, this should be 2 to the n, not 2 to the n plus 1. It's because you're summing up all of these things. And then, conversely, you're saying that if these things are within this distance, then the only possibility is they have to match at the first few digits. I'm going to leave this for you to prove because I think it's a nice exercise in really trying to understand an abstract metric space, right? So you might be used to certain metric spaces like the Euclidean space, right? We have the Euclidean norm, the 2 norm if you want, the vector norm that you're used to, and that also satisfies the triangle inequality. Maybe you've done a little bit more abstract math where you've seen spaces of functions and you talk about the maximum of the function over a compact space. That also satisfies the triangle inequality. This might be your introduction to the first, truly theoretical or sort of, non-tangible, whatever the right words for this might be, version of a metric space. So I want you to try and prove this yourself because I want you to understand it really badly. Here's another thing that I want to introduce, okay? I want to introduce to you the shift map. So let's look at a definition. So let's say the shift map which is going to be called little sigma, and it acts from the sequence space back into the sequence space, is given by, okay, well, I feed in a sequence. So I'm going to feed in S0, S1, S2, S3, so on and so forth. And what I get back is just S1, S2, S3, so on and so forth. So what it does is it chops off the first digit. The way I like to think of this is it's the reverse Cantor's Hotel, right? So maybe you're on YouTube right now. I'm guessing you watch some fun expository things about mathematics, and you probably encountered Cantor's Hotel, this sort of infinite sequence of rooms, and one more person checks in. Well, just move everybody down. You can always make room for them. This is sort of the opposite, right? You have all of these rooms filled up. You kick the first person out, and then you move everybody to the left. And what you can actually show here is sigma, the shift map, is continuous. And again, I'm going to leave this as an exercise for the reader because I think it's a good exercise to sort of work through. But effectively, okay, so I have this colloquial way of talking about continuous. It means that points that start close together stay close together, right? And the way that you're going to prove this is by using this proposition right here, right? You're going to use the epsilon delta definition of continuity. You're going to use the metric here instead of absolute values around things. It's going to be a nice little exercise, but really what I want to try and do is I want to talk about the dynamics, right? So let's talk about the dynamics of sigma on this space, okay? So, based on what we have is we have a metric space of sequences. We have a continuous function acting on those sequences. And what we would like to do is think about iterating orbits under this shift map, okay? This is the same thing as my continuous logistic map from the previous example. In that case, my metric space was the interval 0 to 1 with just this sort of standard absolute value definition of distance. And what do? I iterate it, right? I keep looking at sequences generated by continual iterations of these things. Let's do the same thing here. The first thing I can do is look at the fixed points. What are the fixed points? Well, the fixed points are going to be a sequence that I feed in to get the same sequence out. But this should make sense to us, right? The fixed points are exactly two sequences, the sequence of all zeros and the sequence of all ones. If I feed either one of these sequences into my shift map, all I do is I get rid of the first digit and I arrive at exactly the same sequence. Then what I could do is I could look at period 2 points. Okay. Well, okay, what's a period 2 point? A period 2 point is something that will repeat itself after 2 iterates of the shift map. Well, of course, the fixed points themselves are period 2 points. So there's 2 of them. Now these ones are trivial because they're also fixed points. But there's also 2 other ones, right? There is, and again, you can come up with these, I suspect. This one, 0, 1, 0, 1, 0, 1, 0, 1 forever, right? Because if I take off the first digit, I haven't got back to myself. But if I take off the first 2 digits, I just repeat my sequence again. And similarly, there is 1, 0, 1, 0, 1, 0, 1, 0 forever. Does this make sense? You can probably figure out how many period 3 points there are as well, right? So the period 3 points are going to be, all of the portions of 3 digits, right? So that means that you could have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, right? And so on and so forth. There's going to be 8 of them. And so what you can actually see is an important consequence of this. So, let's make this a proposition, but it's more of just a finding that sigma has 2 to the n period n points. And again, the reason for this is because if you want a period n point, that means you just need to identify the first n digits and then just repeat them to create an infinite sequence. And so how do you choose the first n digits? Everything is 0 or 1. So that's 2 for the first digit, times 2 for the second digit, times 2 for the third digit. That gives you 2 to the n here. Now, what you can also do is look at maybe eventually fixed points. Okay, now this one is, it's pretty simple. But what would an eventually fixed point look like? Well, it would be any sequence that eventually becomes completely solid, right? So, after 4 iterates, this thing arrives at a fixed point. And of course, you can just take any finite stream of digits and then just attach a fixed point on the end of it. And there you go. You've got an eventually fixed point. You could do an eventually period 2 point as well. Just any finite thing of digits and then just attach a period 2 point at the end, right? This is the beauty of the sequence space and the shift map. It is so almost comically easy to analyze, right? We can understand anything in here based on just coming up with really simple little sequences. Now, here's something that I want to talk about. Here's a fun little proposition. Okay, so we're going to use a concept from real analysis again here. But let's say the set of all periodic sequences, right? So all of the fixed points, all of the period 2 points, all of the period 3 points, all of the period 100 points, right? Take them all together and just think of them as a subset of the whole sequence space. And I'm going to call it per of sigma, and that means it's periodic with respect to sigma, is dense in sigma 2. Now again, what does it mean to be dense? Dense means that you can approximate any single sequence in this space with a periodic point, right? Now, the typical example of a dense set that we know is the rational numbers as opposed to the real numbers. The rational numbers are dense in the set of real numbers. We can always approximate pi to a finite decimal expansion, right? Rational numbers are essentially how computers are able to do their computing. If the rational numbers were not dense, we wouldn't be able to approximate certain numbers to certain accuracies. Well, we have basically the same thing in here. We could look at just the set of all periodic sequences, and we could approximate any possible sequence in this space. Now, how do you do that? Well, proof. Let's take a point. Let's take sigma. Let's take a sequence S, pardon me. And it's going to be S0, S1, S2, S3. And what I want to do is I want to approximate this thing to arbitrary accuracy using a periodic point. Well, all I have to do is just take the first n digits and repeat it. So then let's say S star equals to, let's do S0 all the way up to let's do capital N, capital N, and then repeat it. S0 all the way up to capital N, S0 all the way up to capital N, and repeat. Okay, so this thing is a period capital N point, right? So this is a periodic point. And the distance between these two things, well, because they match for the first n digits, I've got this condition right here. And so if you give me an accuracy, you say you want this thing within 1/1,000,000th of it, then I just need to pick capital N large enough, and that will put the distance between these two things to the accuracy you desire, okay? Now, the question here is, are all points going to be periodic under the shift map? And again, you probably know this, right? The answer is very much no, right? You could just think of any non-repeating sequence, right? So just randomly generate 0 and 1 sequences, and with a very high probability that thing is not going to be periodic. For example, convert pi into binary, or at least the decimal digits, 0.14159. Convert that into binary. That thing is not going to be a periodic point. But we know that we can approximate it with a periodic point. What's more is there exists an orbit to this thing that is dense in the whole space. That means that as I iterate it under the dynamics, it comes close to everybody else in the sequence space, okay? So there exists a dense orbit for sigma in the sequence space. And this is a non-periodic point that will come close to every single point in this sequence space under iterations of sigma, okay? So this is sort of a different version of the previous proposition. The previous proposition said I can approximate any element of the space using a periodic point. Now what I'm doing is I'm showing that if I iterate a certain element of this thing, I can approximate every sequence in here as well. And so the proof is actually by construction. Here's what my point is going to look like. I'm going to call it like S. I'll use S star. I know I used it up here, but it was within the proof. So S star, what I'm going to do is I'm going to append every single finite sequence together to make one gigantic sequence. And so that means that my first 2 points in here are going to be the sequences of length 1. So 0, 1. This is a block of one sequence element. Then I'm going to append on all possible sequences of length 2. So 0, 0, 0, 1, 1, 0, 1, 1. Now, before I put anything else on here, if my sequence that I pick randomly starts with a 0, I can get in within 1 of this thing, right? Using just the original S star. If I pick a random sequence from here whose first element is 1, I just have to do one iteration under the map here, and I get within 1 of it. Then, if I pick a random sequence whose first digits are 0, 0, I do 2 iterates of S star, and I've matched the first 2 digits, right? Or then what I can do is I can append all of the possible period, or all the possible strings of length 3, and so on and so forth, right? So for example, if I have if I pick a random element from sigma 2 and it is 1, 0, 1, 0, 1, 0. So that's the first digits of this thing, okay? It has all kinds of junk at the end. All I have to do is keep iterating, so chopping off the first digit until I get to the bits of length 6 and look for the one that I put on the end here. Because all I'm doing is taking the finite numbers of bits chained together and them all the way through. It's an infinite sequence. I can always keep adding stuff in here. Again, think about that sort of Hilbert hotel idea, but this is what a dense orbit will do. Under iterations, this thing comes close to every single element of sigma 2. Now, it turns out, as we're going to see with our fractal set in the logistic map, that it has basically the same properties. And that means that there are a lot of periodic points. Those periodic points are dense. They can approximate everything. And there is a dense orbit inside of that fractal Cantor set from the logistic map as well. And the way that we're going to do this is by establishing a topological conjugacy, a way of saying that the dynamics of the logistic map on my Cantor set is equivalent, is exactly the same, is homeomorphic to the shift map acting on the sequence space. Amazing, right? So I'll see you in the next video when we start talking about that.